everyone to this week's In2Infinity Broadcast with another amazing topic. It's atomic geometry. And I figured today I really wanted to introduce the subject because this is one of the topics that we really have been focusing on with In2Infinity for the last couple of years. And I'm actually going to dedicate the whole September to this topic. But today, I'd like to give you a bit of an introduction what we're actually talking about. So, atomic geometry, it's very important when we think about what actually we're consisting out of, right? So we're consisting out of cells, we're consisting out of molecules, but at the very bottom of it all are atoms, and we would say that's the foundation of matter. Yeah, let's have a look. What the atom actually looks like. There are actually just three components, and that's quite interesting if you think about universal geometry, where we often also start with the Trinity, just as a side note. So, three things, and two of those things are inside the nucleus. So basically the atom consists out of a core, like a nucleus, and so-called shells that surround the nucleus. I always say, think about an onion, right? With like these onion rings. So there are three components, which is the proton and the neutron. Proton in this case are blue and they're positive, so proton, and the neutrons here in white, they are neutral, and these together make actually 99% of the mass of the atom. That's quite amazing if you think about how much space there is in the atom. Then these red things here, they're called electrons, and they're very, very tiny, and they are somewhere in these shells outside. Sometimes it's also called the electron cloud. But that model is just a schematic model. Actually, we have different ideas about the atom, and there's a quite development of hypotheses throughout the ages on what we think the atom looks like. And I'll just give you a very quick and rough overview how we came about to our modern model. So we started with 1897 with the plum pudding model. Basically, the idea was it looks like a plum pudding, yeah, so it's positive with these negative holes in it. This was changed in 1913 and replaced with the Bohr model, which, by the way, is still very important when it comes to today's chemistry, because here we always think about shells. And this very nicely describes the atom as an onion. So basically, you have these electrons in these onion rings. So obviously, for this presentation, we're just going to focus on the electron cloud, not the nucleus itself. But yeah, these were the shells. But the truth is, obviously, again, this is just a very, it's an approach to understand it, but this was still not it. Then 1924, and that model, normally, not a lot of people know about this. It's the pilot wave model by de Broglie, and who suggested that the atom or the electrons, they work as an electron standing wave, and they follow musical principles. And that's an important note here as well, because a lot of the stuff that we're teaching is based on the quadrivium of ancient Greece, and here music, numbers in time, plays a very crucial role together with geometry to understand reality. Right. So then, in 1926, we have the Schrödinger wave model, which basically describes also the electron in terms of waves and explains that they can be located in certain places. And this comes together with the Heisenberg model, which basically says that because the belief was there are waves and particles at the same time, that these particles could not be observed at the same time as their speed. So it was kind of, this probability, basically. They can be located somewhere, but then other places they cannot be located. And that today is the basis of the wave mechanical model. That's the current physicists teach in school or in university rather. Then in 1999 we have another model that is not so known either. It's the MCAS model, and that's a model that it's very closely related also to what we found out, which is more based on geometry. And this is our model We call it atomic geometry. We've been working on it since 2015. And it just shows that we can look at the atom more in 3D, and it gets much more easier to understand how actually elements look like. So this is just to give you an idea that obviously with every experiment and with every research, our ideas change over time. So obviously we have to adjust our thinking as well once we get different ideas how the atom can look like. But here is just an example. This is how these wave functions were determined by basically taking a hydrogen atom, which is the smallest atom there is, and just bombarding them with energy. And they could measure basically where the electrons could be found. And you see already by these pictures that they're quite geometric in nature. Indeed, yeah, we have here circles, we have squares, and we even have hexagons. But let's check this out a little bit more in detail, because sometimes we get quite overwhelmed by all these data, and we always try to say, look at it from a more simplified perspective. So what it is that these electrons, they are subdivided into, you could say, subshells, and they're called orbitals. Just like the planets, they orbit around the sun, you could say the electrons kind of orbit around the nucleus. And there are different symmetries and formations of these orbitals, but one of the key elements is there are only 4. So we have these s orbitals, p, d, and f orbitals, and that's it. Yeah, for all matter in the universe, that's the only orbitals that exist. And you can already see here they're quite simple, and we have actually just simplified them here as well even more. So the s orbital is basically just like a circle, or you could say a sphere. The p orbital, you could say that, just imagine at the center of this x, y, and z axis, there's actually the nucleus, so here's the nucleus. And then here in the p orbital, it means that the electron can be somewhere found in this field, so there's a probability it's somewhere here, or the other one is somewhere on the opposite, exactly opposite, nowhere else. So we would consider this or interpret this as a line, which you will see in a second why we also use the symbol of a triangle, because there are actually 3 of them, and they together form something else. So now with the d orbitals, you already see we have these orbital lobes, and they form actually the symmetry of a square. And there are 3 of those, one at 45 degrees, and there's another one. We're just gonna, for simplification purposes for now, not going into these ones, but just to make it simple, right, we just call it d orbitals, can be represented as a square. Now the f orbitals, you see it already, I already mentioned it before, it's actually like a hexagon. And there are 3 of those again. There's one at 45 degrees, and that's an important one. We see if you study it much more what this actually means. And we have another one here that we're just not going to talk about for today. But these make different geometries as well. We'll just abbreviate the whole f orbitals as a hexagon, as a simplification. So you can see that actually, if you think about orbitals, you could pretty much say the s orbitals form a sphere, a circle, the p form a triangle, d a square, and the f a hexagon. And what does it mean for our periodic table? Now, I know a lot of people might be, oh God, this periodic table is so complicated. Yeah, it is, but actually it's also not. I'm not going to explain everything to you right now, but in general, we have basically 7 shells, and these elements are structured just by numbers. So basically here means 1. 1 means it's just 1 electron and 1 proton. And then 2 means 2 electrons and 2 protons, 3, 4, and so on. And these go through different shells. So what's important here is to notice that there actually are 81 stable elements when we're taking out 43 and 61. I talked about this in another broadcast. These elements here, they go into these rows here. And and they just start to calculate electrons more and more. And you can see that everything that is kind of yellow follows the s orbitals. So they kind of look like spheres in the end. Green follows the square d orbitals, and red the p orbitals, and the blue here the f orbitals. So there is a very, very, very particular order and how these things actually work together. And I would like to bring this in here because sometimes we think about the atom to like, okay, it grows in shells and there's another shell, because that's how it works. No, it just adds up electrons, and by adding, again, always one electron, and obviously something's changing in the nucleus, we go through all the elements of the periodic table. But it's not like the atom is growing and growing into infinity, or at least until the end of the periodic table. The structure is quite interesting if you think about it. So if you think about the first shell, we have the s orbitals, which is a circle here. Yeah, so we have 2 electrons that fit inside, and that's hydrogen and helium. Then in the second shell, we have another s orbital, yeah, so another circle. Then p orbitals, represented as a triangle. In the third, we have s, p, d, and f. So again, an s, a p, and a d is coming together. And on the fourth, we have all of them coming together. But after the fourth shell, what is happening is actually it goes down. So we only have the 3 orbitals, then the 2, and then the 1. So for me, it's a very nice representation, kind of like a hill, isn't it? On the fourth shell, it just finds the tip, yeah, with all the information, and then it goes back down. And that's quite interesting to understand also about the patterns, you know. Everything in nature always follows certain patterns. And there's a very obvious pattern here in the atom. And what does it mean? How can we see actually those p orbitals? So we said a p orbital is like a line, right? So how is the line making a triangle? Well, the p orbitals actually, there are 3, and there are 3 lines that exist on an x, y, and z axis. So this is actually the 3 p orbitals coming together, and you can see they all have a certain symmetry. They're 90 degrees here, 90 degrees there. And if you would just look at the space and you would connect each end of the point together, you will get this shape. And this shape, if you know about universal geometry, you will know that this is the octahedron, and it's one of the 5 Platonic solids. And it has triangles on each face, as well actually as a square in the center. So you can already see here that the p orbital, actually when you put it together, it makes an octahedron. So it's a very simple translation if you think about looking at the atom through a geometric lens. But that's not it. What about the other ones? Right, so while the p orbitals, yeah, as I said, on an x, y, and z axis come together to form the octahedron, we have d orbitals, and I said there are 3 of them that form a square that are exactly the same orientation, so on an x, y, and z axis, and they come together, you can see it here, and they fill, we always say, the internal geometry of a certain shape. So in this case, the internal geometry of a cube. While the 45-degree triangle and this one, we would call this a torus. Yeah, it's basically, in a way, a similar a representation of the torus. We would translate that into the Archimedean solid, the rhombidodecahedron, because you can actually take this shape apart in 3 pieces, and because you can take it apart, it can rotate. So you have a rotation function, which this shape represents. Now the f orbitals, you have again the same pattern. Yeah, you have just with hexagons. So on an x, y, and z axis, 3 hexagons coming together, and they form the internal planes. Yeah, the internal geometry of a cube octahedron, and that's a very, very important shape. A lot of people have been studying this form, including I don't know if you know Nassim Haramein, Buckminster Fuller. So very important shape. And then we said that there are other ones, and we translate these ones actually to the star tetrahedron and the other 45-degree hexagon with the double torus, actually representing the icosahedron, which has a similar function than the rhombidodecahedron, because also here it has 3 parts. You can take it apart, and the central part can rotate, and that's why, yeah, the double torus can be represented in this shape. But obviously, it's much more. There's much more to know about the shapes, but it gives you a very good overview how we can start to look at the atom through geometry. And these 3D geometries are based on, very, very simple forms. I talk a lot about the Platonic solids because these are the most fundamental forms when it comes to symmetry and regularity and everything in equilibrium. Every point is the same distance to the center. And we already saw that the octahedron plays a very, very important role in the atom. It's actually the first shape that comes into existence. The cube was there, and the icosahedron was there. We didn't see the dodecahedron or the tetrahedron. Well, we saw the tetrahedron as the star tetrahedron, but in a sense, certain things we can measure. And there are certain things that we cannot measure, which doesn't mean it doesn't exist, right? That's just a note on the side. So all of these solids seem to play a role, and we'll get into this in our future broadcasts and courses. Now, these are the Archimedean solids, and they're somewhat different to the Platonic solids because the Platonic solids all have the same face, like these are all triangular. This is triangular, this is square, and this is pentagonal. While the Archimedean solids, they consist out of different faces. So here we have the cube octahedron with triangular and square faces, then the truncated octahedron with square faces and hexagonal faces, and so on. And what's interesting is actually these Archimedean solids can be derived from the Platonic solids. That's why we also color-code it like this. So actually, when you chop off the corners of the tetrahedron, you get this shape. You can chop off the corners of this one, you can get this shape. You can also get this shape, and so on. And all of these solids somehow are interlinked in this universal architecture that then reflects in the atom the foundation of our reality. And what's really important to note here is actually the octahedron, which was the first one to be found as p orbitals, which are, by the way, the noble gas neon. And if you think about all the elements of life, like normally, water, carbon, sugar, the air we breathe, most of these elements follow under the first 10 elements of the periodic table. It's I don't know, 80% of the elements or something like that. And they all follow under this very, very simple octahedral structure. So let's say most elements of life are actually not so complicated. Obviously, we have some exceptions like our nutritions, like iron and stuff like that. They are a bit more higher elements. But most of the simple elements that make life, they can just be found in this very simple structure. Obviously, there are normally two spheres inside. And what's amazing about this is, and I talked about this in another broadcast, how space comes into existence, is that this very, very spiritual and very old, very ancient symbol, the seed of life, actually is a template for the three axes that can then rotate to create the first 3D form, which, are actually the 3 p orbitals that can be found along these axes. So, I hope that gave you a very quick and quite a good overview of where we're trying to go with this knowledge. And what's amazing is that a lot more scientists start to think in this way. And I'd like to end here with a quote by Dr. Anthony Garrett Lizzie from the Quantum Gravity Research Institute I think it's in California, and their theory is E8. And what he's saying is, I think the universe is pure geometry, basically a beautiful shape dancing and twisting around over space-time. And with that quote, it actually says it all. They are working on very similar things, where you could actually see it here in the background. That's the E8 structure, where they propose similar things, that basically the atom and space and time, everything can be mapped through geometry. That was a very, very quick one. I hope you just got a sense of where we're going with atomic geometry. It's indeed very, very simple shapes, from 2D, triangles, squares, hexagons, to the 3D Platonic solids and Archimedean solids. Once we can understand how geometries are being created and how they also interact with each other, and the foundation here is really the Platonic solids, so we really have to understand how they're working together and how each shape has actually a particular function. So geometries actually have functions to change and to carry out. And once we understand that, we probably can relate that also to the elements, the different elements of the periodic table and the functions, like why do certain elements transmit electricity, why others don't? Why are noble gases inert and don't react with anything else? And why do actually elements go through reactions? Because there are certain rules, like the octet rule, and if you look at it through the eyes of geometry, it makes much more sense, I think. Yeah, other than that, that's it for today. I'll be back again also next week with another broadcast on solar geometry. So we're going from the atom to the stars. And yeah, just stay tuned. We got a lot more things to share, and very, very excited to finally come online with a lot of the knowledge that we've been working on. Have a good day and have a good night.